Now we're going to do some examples of hypothesis testing for one sample proportion. So let's suppose that we had the situation where we were given a null hypothesis. The population proportion is 0.37, and the alternative is that the population proportion is not 0.37. And we're also given that we took a sample of size 852. Let's do 850 just to make it a little bit easier on the calculations. And that x equals 340 had our characteristics. So in other words, p hat was 340 over 850, which is 0.40. Our test statistic is going to be p hat minus the hypothesized proportion over the square root of the hypothesized proportion over n. So in this case, it's going to be 0.4 minus 0.37 over the square root of 0.37 times 0.63 over 850. If we calculate that, that's 0.03 over 0.0166, which is going to give me a value, and this is a z value, not t, of 1.81. Well, I know I have a two-sided test or a two-tailed test because this is not equal. So let's say I have alpha is 0.05. Well, my critical value then are going to be plus or minus z sub 0.025. I want to find the z value that goes with 0.025 because it's two-sided. I have to split that 0.05 into two pieces. So if I go back to my t table and I look in the infinite row and the 0.025 column, I see 1.96. So I know that z is plus or minus 1.96. So what does that mean? It means here's minus 1.96 and here's plus 1.96. I need to be in either one of those two critical regions to reject my null hypothesis. And I'm sitting here at 1.81. That does not get far enough away from the mean. So we fail to reject the null hypothesis. So the things I want you to take out of this example are one, the calculation of the test statistic. First, notice that it's a z-score rather than a t-score. The p hat comes from the sample proportion. P sub 0 comes from the hypothesized proportion. We use the hypothesized proportion in the denominator here to come up with the standard deviation. Because this was a two-sided test, we did have to divide alpha into two pieces and come up with two critical values, because we would then have two critical regions. And if we lay in either one of these two critical regions, we would reject the null hypothesis. We're not in either one of those, so we fail to reject it. So let's take another example. Let's suppose that we're looking at the null hypothesis is that the population proportion is 0.81, and the alternative is that P is greater than 0.81, and we've sampled, well, let's just make it easy, 1,000 people, and the number with the characteristic is 835. Then P hat would be 835 over 1,000, which is 0.835. Our z-score, our test statistic, z, is P hat minus P naught over the square root of P naught times 1 minus P naught over n, which in this case is 0.835 times 0.835 minus 0.81 over the square root of 0.81 times 0.19 over 1,000, which equals, that would be 0.025 over 0.0124 is 2.02. I round to 2 decimal places. And again, let's use alpha is 0.05. Because I have a one-sided test now, that whole 5% will go in one tail. So we will use the 0.05 column here and look at the infinity row, and that gives me 1.645. Since 2.02 is greater than 1.645, we reject the null hypothesis. We conclude that P is bigger than 0.81. And again, don't get confused between P used for proportion and P for p-value. In the hypothesis aspect of it, we're saying that the proportion is greater than 0.81. If I want the p-value, that's the probability that z is bigger than 2.02, which is 1 minus the probability that z is less than 2.02. So I can go to my normal table. I can look up to 0.02, and I see that's 0.9783. So this is 1 minus 0.9783, which gives me 0.02 2.17 because I would have a 2.17% chance of observing this sample, and that is less than my 5% chance. That I get for alpha, then I know that I will reject the null hypothesis. So that concludes examples for hypothesis testing for proportions, at least the hand calculations of it. If I want to test a hypothesis in StatCrunch for a proportion, I can go to Stat, Proportion Stats, one sample with summary. I can type in the number of successes and the number of observations, the hypothesized proportion. I wanted to know if I was greater than that, and I'll hit compute, and notice I get the same values. Here I have a t-value of 2.015. Well, I can't do 2.015 on my table, so I rounded to 2.02. And the p-value is roughly what we calculated as well. 0.0219 is the actual value because they can go to more decimal places than we could. We were stuck with the table, so we had to estimate it at 0.0217. That should help you with your homework and the lab.